and have two different lines. So this is not allowed, is what theorem 2 says. Okay, moving right along. Theorem 3, theorem 3 says, given a line in a plane, there is a point in the plane which is not on the line. Why should that be true? Well, you have this line, L, and we're given a line in a plane. There's a point in the plane. So I want a theorem that says there's always a point in any plane which is not on a line, given a particular line. Well, there are then there's a point in the plane which is not, so now what do we do? Oh, yeah, duh. We invoke this axiom 1, which says there's like a bunch of stuff. In particular, every plane has two lines. Well, if every plane has two lines, and L is one of the lines, then there's always got to be another line. And what are the options? The options are this other line that axiom 1 stipulates must exist, could be a line which is parallel to L, in which case and different. This is a different parallel line. In which case, because every line has points on it, there's at least one point on M, and L and M have no points in common, so this point must be off L. And on the other hand, if this second line that must exist is intersecting L, well, now I have a point of intersection, and then since every line has 2 points, there's a point over here, another point on M that's not A, and well, since L and M can intersect at most 1 point, then that means L doesn't go through B, because that would be not allowed. And since L doesn't go through B, well, there's your point which is not on line L. Okay, at some point I can't do all of these, this is going to take forever, so I'll just say some out loud because they're maybe not that exciting. For a given point on a given line in a given plane, there exists a different line in that plane through that point. Whoa. In other words, if you have a line L and you have a point A which is on that line L, then there's another line which goes through A. Okay, I'll leave you to think about why that's true. Oh, here's the proof. The proof says, dude, the previous theorem says there's a point off that line, and now since there's a line through every 2 points, then you just connect them, and there you go. Now there's a line through A. This was theorem 4. Theorem 5, will he just keep going or will he stop? For a given line in a given plane, there exists in that plane at least one different line parallel to the first. Okay, so now we have a line, and we have to say, oh, there's always another line parallel to L. Why is that true? Why is that true? Oh, well, this theorem 3 again says that there's always a point, given any line, there's always a point which is off that line, and now we invoke, finally, the parallel postulate, which says that given any line and a point, that there is a parallel line, and so that shows that there's always a parallel line. Let's keep going until we run out of board space. Theorem 6 says, for a given line in a given plane, there is a line in that plane not containing that point. So if you have a line, and you have for a given point in a given plane, there's a line in that plane not containing. Oh, sorry. This says, given a point, just out there, just chilling, there's always got to be another line that doesn't go through A. Why is that? Well, axiom 1 says there's at least another point somewhere, call it B. Then, there's some line through them, call it L. Now, I once again say, by, I guess, the previous theorem? I'm not really paying attention to what's going on here. By some theorem that I guess I already proved, there's a line through B. There's another line through point B on line L. And now, whatever that line is, A can't be on it. Because then these two different lines would both intersect at 2 different points. So given any point, there's always a line that doesn't go through that point. Okay, this may be a good place to stop. This entire thing I'm talking about right now is a summary of a unit of a class that kind of no longer exists, that I taught 10 years ago. So, okay, this is very obscure, but I promise it's going somewhere helpful, or at least I think it is. Okay, Are there more interesting theorems worth talking about? Maybe not. Given any plane, every point must belong to at least two lines, is theorem 7. Given a point, there's always two lines through that point at least. I'll stop now the proofs. Theorem 8, theorem 9, in fact says, theorem 9 says that in fact, given a line, there are always 2 points which are off that line, and that's because there's always a parallel line, and that parallel line always has 2 points off it. And more, and more, and more, and more. Eventually, we get to this theorem 13, and we just slowly prove these out in extreme levels of detail. In theorem 13, which says, in fact, there have to be at least 4 points, no 3 of which are collinear. So, there are 4 points, what I am going to call the core 4, which have the property that that there's no line which goes through 3 of those points. And, okay, I'll just say that. I'll just move on. Blah, 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 blah. Eventually we prove various famous things, such as if you have a line and you have if you have a parallel line and you have one line which intersects one parallel line, then it must intersect the other. A line intersecting one parallel line must also intersect the other. Then you have the transitivity of parallelism, which says that if, which is kind of a contrapositive of this or something like that. It says that if 2 lines are parallel and 2 other lines are parallel, then they're all parallel. And finally, okay, we're getting to the end now. We prove the sort of grand conclusion of all of this is theorem 16 and 17, which says that in fact all pairs of parallel lines, if 2 lines are parallel, then they must have the same number of points. Because if a certain line has a certain number of points, then through each of those points there is like another line, and that other line must intersect the parallel line by sort of this previous theorem 14, and so that creates a point, and then you just keep doing that. And so somehow the existence of a given number of points on a given line ensures that there are the same number of points on any other parallel line. And I think I haven't exactly explained why that's so, but I've shown that sort of for each of these there must be a new point on this line, and it works in the other direction too, right? There can't be like a 4th point on this lower line, because if so, it would create a 4th point on the original. Okay, but I gave a very careful argument of all this. Alright, that was the theoretical portion of this unit on affine geometry, and we sort of did all that, and yet still, children, and yet still sort of stopped short of the full intended curriculum. The full intended curriculum that I was following was to, hi Ada, was to, after having established that there are the same number of points per line, we can then start considering establishing axes. And so you could have a line and another line which intersects it, and then you could say, okay, well, let this have, 10 points or something like that. Well, if this line has 10 points, then there's a parallel line which also has, 10 points or something. Maybe 10's a bad example. Let me use 7. And then...
Papa, stop doing your work!
No, I'm not going to stop doing my work, Ada. I'm going to keep doing it.
Not for much longer.
And so, in fact, now we have these other lines are also parallel, and so what we have here now is a grid. In fact, if you think of this as 0, 0, what we have going here is this sort of proof at like an extremely low level of the existence of this lattice. And having sort of derived the geometry of this lattice axiomatically, we then proceed to give coordinates to all the points of this lattice, and then
yes,
after that,
yes, Abby.
oh, the,
Yes, Abby, up here.
last time we were up here, yeah, there's a 2-year-old on screen now. I'm not stopping though. Okay, and this was somehow meant to be an introduction for the first time at a theoretical level to the concept of a plane and of coordinate geometry. Okay, dwelling on this for a minute more, so that was the sort of theoretical side of affine geometry. How about the more concrete side of it? This is still me summarizing this thing I used to do 10 years ago. What does one model of affine geometry look like? Well, what is a model? That's a kind of an advanced concept. A model is an example which satisfies the axioms. So, what's one way we can satisfy the axioms of affine geometry? Well, one way is if every line, if there have to be at least 2 lines in every plane, or rather, if there's a line and there's a line parallel to it, then and every line has 2 points, perhaps we can get away with every line having just 2 points. And the answer is we can. Call this point P1, call this point P2, P3, and P4. And this is the simplest model possible. The simplest model possible is called the 4-point model. And the 4-point model, as I taught the 9th graders once upon a time, has 4 points, call them P1, P2, P3, P4, and now it has a bunch of lines. Well, here are 2 lines. Let's call this line L1 and call this line L2. Now I will use some different colors like blue. Then there must be a line through these 2 points, so that's like another line and another line, so that's like L3 and that's L4. And now now I sort of blow the mind of the children a little bit by saying that, well, there must be a line through P1 and P4. And so let's draw that line. Let's call this line L5. And then there must also be a line between P2 and P3. Now, if I draw this line P2 and P3, casual people will say, oh, these 2 lines intersect. But no, in fact, this line L5 and L6 are parallel. And they're parallel because 2 lines are parallel if they have no points in common. And in fact, L5 and L6 have no points in common. L6 has points P2 and P3 on it, L5 has points P1 and P4 on it, and so they share no points. Now, the part that requires an advanced level of abstraction, maybe not hard for you guys, is that the line is uniquely determined by the points that are on it. This model is given by the explicit list of the points and the lines, which is to say that this is just, this picture that I'm making here is not really the model. This picture is just a visual representation of the model. The true model is just sort of coded in as a kind of a discrete object. The line is determined by the set of points that are on it. The picture is just here to sort of satisfy our visual need for some kind of understanding. But these lines really are finite. Each of these lines consists of exactly 2 points. And so this is an example of a finite geometry. It's a geometry in which there are precisely 4 points, precisely 6 lines. And if you don't like this way of doing it, you can always draw your line L5 looking like this. And perhaps you like that better because now lines L5 and L6 are parallel in the sense that they're not, that the marks on the paper are not intersecting each other, and also they're sort of pointing in the same direction. But of course now we've obliterated any concept of lines being straight or anything like that. All of those concepts are irrelevant here. Okay, and now you can go through and verify that this model actually satisfies the axioms. Are there at least 2 lines in this plane? Of course there are. There are 6. Are there at least 2 points on every line? Yes, there are. Is it true that through every 2 points there is a line? Well, yes. In fact, we have 4 points, and okay, I didn't tell this to the 9th graders, but now you know, because this is a discrete math class. If there are 4 points, and there's a line through every 2 points, then there are 4 choose 2 ways of picking a pair of points out of the 4 points, and 4 choose 2 is 6. So there it is. finally, the parallel postulate holds. Because for any given line and any point not on it, there's exactly one line through it. So what we have now really, this color choice maybe is poor. I don't know if you can see the difference between purple, blue, and black. But what we have here are these pairs of parallel lines. And so L1 is parallel to L2. And L3 is parallel to L4. So I'll maybe now do two of these little arrows. And and then the purple lines are parallel. In other words, these 6 lines, one second, these 6 lines naturally organize themselves into equivalence classes. We talked about this earlier in the semester. An equivalence class is or rather, an equivalence relation is a relation which is symmetric, transitive, and reflexive. And because we have defined parallelism in our this sort of idiosyncratic way, such that every line is parallel to itself, then consider the relation of parallelism. L1 is parallel to itself, and also L1 is parallel to L2. So if every line is parallel to itself, that means that the reflexive property holds. The symmetric property just says that if L1 is parallel to L2, then L2 is parallel to L1. Of course that's true, because we've defined parallelism as having no points in common, so it works both ways. And then the transitive property as well is a theorem that we actually proved. And so parallelism is an equivalence relation. An equivalence relation on a set of objects partitions that set of objects into equivalence classes. Equivalence classes are subsets for which all the members are equivalent, which in this case means parallel. And so we have a pair of parallel lines, another pair of parallel lines, and another pair of parallel lines. Okay, so some advanced things going on here. Okay, let's do one more. There's the 9-point model. What is the 9-point model? Well, it's the model in which there are 3 points on every line, and you're sort of free to have as many points on the line as you want. This is one model, but there are many models that satisfy these axioms. For example, there's the model in which, well, I'll just, without going through the details of it, by using all the previous theorems, once we know that there are 3 points per line, then we can, well, I'll just draw the picture. Here are my 9 points. Let's not bother labeling them. And now let's look at all of the possible lines. Well, through every 2 points there must be a line. So let's call this a line, and this is another line, and this is another line. So the 3 green lines are all parallel to each other. That's one equivalence class of parallel lines. And now we have another pair of parallel lines, another equivalence class of parallel lines, all of these. And those 3 red lines are all parallel to each other. And then we have more, and here's where it gets kind of exciting. We have the blue ones, which look like this. And now if you want to sort of draw the line so that it's more clear what's going on, then you want to do something like this, where now there's going to be another line that cuts through these 2 points, and now of course the line can't go through any of these 3 points because those 3 points are already taken. So the line must be, and this new line that I'm drawing is meant to be parallel to the first blue one. But it also can't go through this point, because if it went through this point, well, I already have a line through these 2 points, say, and I already have a line through these 2 points, and so it has to be this sort of other point. Okay, and then finally we have this. Alright, and so in fact, this is now my 3rd equivalence class of parallel lines. These 3 lines are all parallel to each other. There are 3 lines in this equivalence class, in this blue one, and there are 3 points per line. Of course, you use up all the points. Each equivalence class, each of the lines in a particular equivalence class go through every single one of the points. Okay, and then finally, I guess I'll do this one in black, you have the other one, which comes down like this, and then like this, and then like that. Alright, behold the 9-point model. this model has 9. In this universe, there are 9 points. There are 3 points per line. There are 4 lines through every point. And there are 4 equivalence classes of parallel lines with 3 lines per equivalence class. And 12 lines in total. Okay, and let's just sort of let's just kind of clarify this conversation. Oh, and so this is another model of the axioms of an affine geometry. Okay, and so we have let's try to explain what's going on here in a kind of combinatorial way. So we're here now. We have we're sort of free to choose how many points there are per line, and we are free to choose how many lines. Well, so what options have we seen? We've seen that there could be 2 points per line, such as in this model, or 3 points per line, such as in this model, and then let's imagine that there are n points per line to do it kind of in general. Now, how many lines are there through each point? Okay, this is kind of subtle. Here we've just seen that there are going to be 3. Here we've just seen that there are going to be 4 lines through each point. And so it seems that there's always going to be n plus 1 lines through every single point in this model. And that's just true. Because if you give me some line, arbitrary line, and this line has precisely n points on it. Okay, so suppose there are n of these points, and now you give me some point which is off that line. Well then, what can I say about the number of lines which go through point A? Well, there's going to be 1 line through A, connecting each of the points on this line L, so that's n. But then there's the parallel one. Then there's the one that's through A parallel to L. So that's a sort of a rough proof that there are in fact going to be n plus 1 lines through any given point, if we insist that there are n points per line. Okay, that was pretty good. How many equivalence classes of parallel lines are there? There's also always going to be 1 more. Here we saw that there were 3 equivalence classes of parallel lines. Here 4, and in fact it's just always going to be n plus 1. Why? Well, I guess it's just a follow-up on what we said here, right? If there are this many lines through a given point, if you have a certain point, and there are n plus 1 lines that go through that point, well, then none of those lines are parallel to each other, and so there are at least n plus 1 sort of categories of lines which are all parallel, because none of these lines can be parallel to each other. Okay, that was a rough, loose explanation. How many lines are there per equivalence class? Alright, kind of like losing track of the argument here a little bit. Well, here we've just seen that there are 2 lines per equivalence class. Here we've seen that there are 3 lines per equivalence class. Why do we know that is true? Well, I guess it's because if you have a line and you have an intersecting line, and you're in a world where there are always n points per line, then every one of the points on this new intersecting line, call it M, by the parallel postulate, there's always like a line parallel to L through each of those points. And so this seems fairly clear that there are going to in fact be n lines per equivalence class, because for any given transversal, it will have a certain number of points, and there's a parallel line through each of those points. Okay, and finally, we can talk about the total number of points and the total number of lines. This is either subtle or I'm going to explain it poorly, but if there are 2 points per line, and there are this many lines per equivalence class, well, that's what an equivalence class is going to go through every single point. Or rather, the equivalence relation of parallelism will partition the entire model up into equivalence classes. And so once you have a whole bunch of parallel lines, those parallel lines, those lines that are all parallel to each other, must in fact go through every single point in your model. Because if there was just some loose point out there floating around that none of these parallel lines went through, well then, by the parallel postulate, there would be another line through that point parallel to each of these. And so in fact, if there are this many points, if there are 2 points per line, and there are 2 lines per equivalence class, then if you multiply these 2 columns, then you get that there are just going to be 4 points total in any given set of parallel lines. And that equivalence class of parallel lines is going to go through every single point in your model. And that means you're always going to have a square number of points in your model. And it's always going to be the square of this sort of free parameter. So we have n squared points, and how many lines are there? This one I think is easier, right? If you have 3 equivalence classes of parallel lines and there are 2 lines per equivalence class, then you just multiply these 2 columns, and in fact you get 6 lines in this model. And in this model you get 3 points per equivalence, 3 points per line, 4 lines, 4 equivalence classes of parallel lines, and 3 lines per equivalence class, so you get 12 lines, and in general you're going to get n plus 1 lines. So in this sort of arbitrary model of an affine geometry, a finite affine geometry, following those axioms, you can prove as the kind of culmination of this unit that you're always going to have, if you have a certain every line must have the same number of points on it, and if that number is n, then you can prove sort of each of these facts. This is sort of very combinatorial. Okay, the last thing is that you can assign actual, maybe I'll stop there. You can assign equations to all of these lines even. So if you call this point 0, 0, and you call this point 1, 0, and you call this point 2, 0 in the kind of traditional way, and this is 0, 1, and this is 0, 2. In other words, establish a coordinate system, a kind of a finite coordinate system. This is 1, 1, 1, 2, 2, 2. I need to stop this video very soon. 2, 1. Then we can talk about this horizontal green line here, for example, is just the line y equals 0. And this is the line y equals 1. And this is the line y equals 2. Okay, it's just that's just nothing new, so I won't comment on it. This is the line x equals 0. This is the line x equals 1. And this is the line x equals 2. Okay, then it gets kind of more interesting. In fact, this black line that goes through 1, 1, 0, 2, and 2, 0 is perhaps the easiest next one to describe. It's the line with, we would say in a normal Algebra 1 classroom, slope -1. But that means I can write it as x plus y equals 2. I think I did that right. Yeah, it's the line x plus y equals 2. And this will be the line x plus y equals 1. And this will be the line x plus y equals 0. Now notice, if you want to call this line here, this one, x plus y equals 1, then that works perfectly well with the point 1, 0 and the point 0, 1. But you also need it to be the correct equation for this point 2, 2. Okay, well, sophisticated people who experience number theory like yourselves will recognize that the point 2, 2 is on the line x plus y equals 1 if you are doing this entire model in Z3. Z3 is the group in which we have just 3 elements, 0, 1, and 2. And addition works in the way you would expect, such that 2 plus 2 is just 1, because you just do everything mod 3. And you also have, in this system, multiplication. Because you need that for when you get to, say, this line. This is the line 0, 0, 1, 1, 2, 2. This is the last one I'll do. This blue line that we would normally think of as the line y equals x. But we don't have the line y equals x anymore because we have no negative numbers. So this is in fact y plus 2x equals 0. I think I did that right. Yeah. 0, 0 certainly satisfies it. 1, 1 satisfies it because you get 1 plus, and 2 times 1 is 2, and so you get 0. But 2, 2 also satisfies it because 2 times 2 is 4, but mod 3 that's 1 plus another 2 is 3, mod 3 that's 0. And so without using negative numbers, in fact what you have is a line for every possible linear combination of x and y, where x and y are not both 0, and the coefficients are drawn from the set Z3. Okay, so there's a lot going on here. Finite geometries, modular arithmetic, sort of advanced counting principles, equivalence classes, etc. And if you had taken this class with me 10 years ago, you would then know about all of these things. I think this is worth it because everything we're about to do in this unit is just this, but done slightly more carefully and more quickly, and not on an affine geometry, but instead on a projective geometry. And here's where I'll stop and do some childcare and finish this video later this afternoon. Goodbye.